An hypothetical relay between Tuscany guy. We have now Dr. Luca RUGGIERO, that is from Tuscany actually, but he moved a little bit around the world. So right now he's still seated at the University of Konstanz, but he will move in a few days. What are you looking for? Here is the pointer, and then you have to push the button in order to go ahead. Okay, so Dr. Luca RUGGIERO, he is in the Marcus Gruber lab just for a few weeks more, and there he studied a lot, I would say, bigger animals than the Miocene of before. So the limits of explosive strength in human muscle. Go ahead, Luca.
Così vai avanti, ecco il punto.
So, I should start with two things. First, I'm not in the wrong meeting. Yeah. So, I should start with two things. First, I'm not in the wrong meeting with this question. And second, I'm the only thing keeping you away from lunch, so I will try to be quick. This is really the question that got me started in this project. Like, can elephants jump? Well, at least this is the question I got in a few weeks. And the deeper question is actually what the limit is for explosive strength from tiny shrews that are 2 grams to huge elephants that can be 5,000 to 6,000, 7,000 kilos. So I decided we start with the species I know best, which is humans, and that I work most. First of all, what is the relevance of explosive strength? So explosive strength can be measured with the rate of force or torque development or RFD, and that's the first derivative of force, and that's directly proportional to the rate of acceleration. So the higher the explosive strength is, the higher the RFD, and the higher the rate of acceleration. To figure out the question, to have something that was scalable across 7 orders of body sizes, I had to start from modeling. I started from the human species. As a muscle, I had a heel-type muscle model. Then I will go through the modeling data, the input variables, and then the validations and simulations. Regarding the muscle model, this was something that allowed me to change the firing frequency of the motor units and to also scale or properties that I wanted. So it's the model developed by Wexler et al. 1997, and the first equation takes care of the calcium troponin complex, and then it's actually the second question that does the development of force of the differential equation. How I optimize the model and found the parameters, I use data from 13 participants from ankle dorsiflexor muscles. The beauty of this muscle is that you can use any stimulation frequency you want with any intensity you want because it's not painful at all. So I use data of 10 Hz strains, 100 Hz tetani, and then catch-like property so that I could actually simulate the mean properties, force-frequency relationship, and catch-like of the human muscle, or at least the functional properties. As input variables, I had to model motor unit discharge rate, so I used the bi-exponential function with 2 components, fast and slow. I use high-density mg data from explosive contraction, 158 motor units from 34 participants, and I found the tau from this second-order differential equation, and that's the discharge rate function of motor units to simulate the spike frequency adaptation, and starting from a firing rate of 120 to 25 Hz, which are very plausible values for human motor units in ballistic contractions. I also had to choose a different number of motor units because motor units do scale between species. For humans, I use 150 motor units because these are measured values in the material, so that I could have, I could take into account also a different number of motor units. So here are the results of the model. On the right side, you can see the different motor unit recruitment speeds, which is in motor units per second. So it goes from 200 to 12,000. And as we increase the motor unit recruitment rate, the RFD increases, and also with 12,000, when we have almost full synchronization with motor units, we can also see the individual twitches. which was about 25-30 Hertz. If we zoom within the first 150 milliseconds, we can see there is a huge difference. Again, as we increase motor units recruitment rate, RFD increases. From here, usually what we do in human participants is that we take the rate of force development in the first 50 milliseconds, in the first 100 milliseconds, and then 150 milliseconds, and we can also take an increasing window from 0, going millisecond by millisecond, and get a rate of force development function. So these are the results, and this is the slide where I will stay for a while. We have the rate of force development at 50 milliseconds in blue, and how it increases with the recruitment rate, the one at 100 milliseconds, and then at 150 milliseconds in light blue. And then the black dashed line is the rate of force development function, the one of by increasing the window millisecond by millisecond. The dots are real data from real participants, so the model could actually reproduce very well explosive contractions. The vertical dotted line and the gray area are the mean values, what has been found of motor unit recruitment speed, plus minus 1 standard deviation. So we can see that there is a limit to explosive strength in human muscle, which is about 6 maximal voluntary forces per second. This limit is achieved sooner than we expect, so it's achieved even within physiological values of motor unit recruitment rates, very common values. There are also other two things. This number 6 can be 7 or 8 in the quads, or even up to 9 for biceps brachii, so it can change between muscles. So here we also have two things to talk about. The first one is that if someone is within this area, in terms of motor unit recruitment rate, it makes sense to train it. And these usually are untrained participants, or elderlies, or inactive, so it makes sense to train it. So that with the even small increase in motor unit recruitment rate, we can have a huge gain in explosive strength. But if someone is here, and these are healthy people, but normally in this range there are athletes, where we are usually here, we cannot get gains in explosive strength by increasing motor unit recruitment rate, and we have to train either maximal strength or find other ways like motor variability or intermuscular coordination, all strategies that coaches actually already know. So that was all from my side. Thank you for listening.
Thank you, Luca. Very interesting model. Who has the power for asking? He arrived.
Polish University of Basel. But can elephants jump? I was very intrigued by the question, but you didn't answer it.
Yeah, that's so I will let you know maybe in 1 year or so as I move on. I think the problem of them is not so much in jumping, but in landing. So everything is scalable. It's even scaled the amount of work that they can produce. Of course, they would deal with more potential energy, but that's doable. I think their biggest problem is landing and or dealing with decelerations in general, because everything can scale, size of the muscle fiber, shortening length, and so on. The thing that doesn't scale in mammals is nerve conduction velocity, which is the same from tiny shrews to elephants. And since the elephant is very big, then it would take a lot of time for sensory motor control for the signal to get to the brain or to the spinal cord and back. And I do think that's what limits fast performance in giant animals on Earth.
Be careful.
Yeah, Daniel Lavori, University Bochum. Hi Luca, thanks for the talk. You said the maximum rate of force development is 6 times MVC per second.
For this specific muscle group, ankle flexors, when there are other muscle groups, depending on the architecture of the muscle, this may increase.
Okay, so you already answered my question, thank you. Because I want to ask how you consider the tendon and the architecture, or is this a muscle value or muscle tendon unit value?
So, where to start? So I start from the limitations. That's one of the limitations. So what stiffness or tendon and yield ratio of the muscle, which it is an important determinant of rate of force development. This model does not count for that. And elbow flexors, about 8 times the MVC, the extensors 4 to 5, and tibialis anterior, the maximum limit 6. So yeah, it will change between muscle groups.
One more quick question. If not, stay there. Stay there. It's not my fault. There are 2 scientific advertisements right now. So please, Professor Ferretti, fast here.